Welcome to CppChat. I think we're going to have a great show today, but first I'm going to read our disclaimer. The products and claims made about specific products on or through this site have not been evaluated by the United States Food and Drug Administration and are not approved to diagnose, treat, cure, or prevent disease. This site is not intended to provide diagnosis, treatment, or medical advice. All right, we got a great show, I think, coming up. We have two guests who've been on before, and I'm going to let them introduce themselves. Howard, do you want to say a little bit about what you do?
My name is Howard Hinnant. I work for Ripple. It's a software company located in San Francisco. We're in the international financial bank settlements business. We're doing this with digital currencies. We have our own digital currency, XRP. It's like Bitcoin. And it's an exciting job, and I'm really excited to be there, and we're going to change the world.
We were just chatting about that, and I didn't realize, I knew that Ripple had a currency, at least I thought they did, but the Ripple currency market cap is about a quarter of Bitcoin. So it's not just another, I mean, there's lots of currencies out there. I mean, there's
hundreds.
Yeah, there's lots of them, but Ripple is a significant size of that.
Yes, we're doing quite well, and we're executing well on our strategy, and it's a fantastic team that I work with.
All right, that's great. All right, so we also have who's on the special episode at C++ Now, Malte. Malte, yes. You want to say a little bit about what you do?
Sure. I'm Malte Skarupke. I am an AI programmer at Avalanche Studios in New York. We work on video games, and yeah, I'm here because I gave a talk at C++ Now about sorting, about using Radix sort for a lot of applications where you classically use standard sort, like generalizing Radix sort for more use cases.
Right. So yeah, as you might expect, this is the show we're going to talk about. We're going to talk about algorithms, right? So the first thing I want to talk about, before I knew anything about Radix sort, I was introduced to, it was actually Scott Myers who pointed out to me that a fellow named Thomas Guest on his blog, can't remember the name of his blog now, but we have a link in the show notes for the episode. But the name of the blog was Top 10%, and the idea was that he wanted to have a range of integers. He was working, this is all test data, right? So he's working with a bunch of integers, and he wanted to sort the top 10%. Now, the way you would assume to do that is to call partial sort in the standard library. But he discovered that, first of all, kind of surprisingly, partial sort isn't always faster than a full sort. Now, it actually makes sense if you think about it, because full sort, of course, is the fastest possible way that we can do a sort. And a partial sort is a less efficient algorithm, but it has the advantage that you can stop it before it does the full sort. You can just do the partial sort, right? But eventually, with enough data, the faster algorithm is going to outperform a slower algorithm, even when the slower algorithm is doing less work. So what he found out is that about 20 million integers, it's actually faster to do a full sort than to do a partial sort of the top 10. That's kind of surprising, but we don't often sort 20 million integers. The real surprising thing was that he found out that if you do an nth element first and pull, so what nth element is, for people who aren't familiar with that, nth element, you give it a range of data, and you give it a position, give it an iterator to a particular position. And what the algorithm does is I don't want to say sort, because it's not a complete sort. It shuffles, it moves data in this range such that the item that you've given an iterator to will be the correct item if everything was sorted. So if you point at the 10th element, then that 10th element is the element that would be there if everything was sorted. And in addition to that, everything that comes before that element are things, not necessarily in any particular order, but those are the things that would be before that element if it were completely sorted. And of course, everything after that is after that. So it essentially partitions the data into things that would be before it and things that would be after it, and then the partition point is the exact element in the correct point. So if you call nth element at the 10% mark and then do a full sort on that, on the first 10%, you have done the same work, you've gotten the same result as calling partial sort. However, in his tests, it was dramatically faster, not a little faster, dramatically faster. So the question is, why does the standard library not do that? It doesn't seem to me there's any reason the standard library couldn't do that. And so I've wanted to ask this question of Howard for a very long time, because Howard, to me, is the guy for the standard library implementation. So Howard, here's my chance. And for those of you who are wondering, I've not yet asked Howard this question, so I'm getting this answer for the first time. Howard, why does the standard library not implement partial sort using nth element followed by full sort?
You know, I'm going to have to guess, because the real person to ask for this would be Alex Stepanov, since he brought us the algorithms and the standard library. But basically, partial sort is based on heap sort. The standard algorithms contain several sorts, not just sort, but stable sort, heap sort, et cetera, et cetera. And so partial sort is based on heap sort, where you just stuff it into the heap, and then you pull out the first, however many you need, and sort them as you go. And if we stop talking about partial sort for a moment and just talking about full sorts, if you sort something with heap sort and sort something with sort, which is based on quick sort, you'll obviously get two different algorithms, two different speeds, and quick sort is not always, but almost always faster than heap sort. It does have worst case order n squared. Sort is specified such that if you do tend toward that worst case scenario, it's supposed to switch over to something like heap sort internally halfway through to keep itself from going to n squared.
Somehow you can detect that you're in that worst case situation and you can correct.
I'm sorry, what was the question?
What I said is, somehow you can detect that you're in that worst case situation where you would be looking at n squared, and you can switch over.
Right.
Yeah, you count the number of recursions. Like, you count how often did quicksort have to recurse, and if it recurses too often, you just switch over to heap sort.
Exactly.
Okay. Now let me ask you this.
Okay.
Does the standard actually say you do that, or is it that's the only way you can get the performance that the standard mandates? Or
for standard sort, there's actually a lot of leeway. It says do your best, and on average, no, on maximum, you can't have order n squared. You've got to do better than order n squared. I don't remember exactly how it says it, but I think it says complexity is n log n or something like that.
Okay. Okay. Which quicksort doesn't necessarily guarantee. In worst case, quicksort's bad. In normal case, quicksort earns its name quicksort, right? I mean, it's
right. So partial sort, for probably purely historic reasons, is typically implemented on top of heap sort. Nth element is a quicksort algorithm, though. That's done purely with the quicksort technique, and it doesn't have the switch over to. It doesn't have the requirements that it has to switch over to heap sort if it starts to go n squared. So actually, there are probably rare cases where the nth element plus sort would give you very bad answers. But
I see.
Those are likely rare cases, because there's all kinds of things you can do with quicksort to make those bad cases very unlikely, like using median of 3, or median of 5 to choose your pivot and stuff like that. Also, the relative performance of these algorithms, partial sort versus nth element, is very sensitive to the ratio. This top 10% blog fixated on 10%, but if you go to small ratios, even smaller ratios, 1%, say, or something like that, you'll run into a situation where partial sort will consistently beat this other algorithm. And if you go to higher ratios, say greater than 50%, sort is always going to win. So it's very sensitive to the percentage of elements that you're.
No, wait a minute. Okay, so if instead of doing the top 10%, you did a much smaller 1% or 3%, something smaller.
Something smaller.
You're saying that that's actually going to start to favor the heap sort approach, the partial sort?
Yes.
Okay. Now that surprises me because nth element, I think that the standard says nth element will, in average case, be order n.
Right.
Right. And so the expensive part is that you're having to do a full sort of that top 10%. And you're saying if you make that smaller, that's even worse for this approach?
Well, it's not worse for the approach. It's just that the partial sort based on heap sort will start getting more favor because creating a heap is pretty cheap. I don't remember the exact. That may be order n, may keep. I would have to look that up. I don't know.
Okay, so then the other side of that is what you said is at more than 50%. You said sort wins. Now, what did you mean by that? You mean a full sort?
Yeah. Now, don't take 50% in concrete. Maybe it's 60, maybe it's 70. I don't know. But at some point, you're better off just sorting the whole thing
rather than calling partial sort.
Right.
Which is kind of what he said. Even at 10%, if you have 20 million integers, it's better to just call a full sort because quick sort's fast, right? So quick sort is going to beat heap sort in the general case. It's only when you have a lot less work to do that heap sort could possibly win, right?
Right. Although with the nth element thing, you're doing a quick sort there again too. But there you're specializing on just trying to get the nth element.
Okay, so let me ask you this then.
So, actually, it's really quick. So this week I actually tried to reproduce the experiment. Well, like one thing, if you have the page open up from the top 10%, he doesn't show like on the x-axis it's just a linear scale. So like I'm really interested in the bottom left corner of that graph where of less than 1 million elements. So I tried to producing it myself and just do a graph of having a log scale on the x-axis. And first, what I found is so on my machine, partial sort actually stays faster than full sort for up to 100 million elements, and it's always slower than nth element, no matter how small it is. I also actually just now, as you said, it's faster for if you're looking for a smaller percentage, like this is the top 1%. I just changed my code and reran the benchmark, and it's actually even then the nth element is faster, even if you just want to look for the top 1%. Even then it's faster than partial sort. At least in my simple test example, just sorting random integers.
Interesting.
Yeah. So let me ask you this, Howard. I mean, the standard doesn't say how anything's implemented, right? So as a standard implementer, you could do something like you could say, I mean, you have to be given random access iterators anyway. So you could say, what is the percent that I'm trying to do a partial sort of? And I mean, as you said, Alex originally implemented this with heap sort. But we're not bound by that. I mean, you can implement this any way you want, right? So you could, in fact, write, change the standard implementation on your library. You could change it to detect this and say, oh, look, we're doing something, and you figure out what the sweet spot is. It's something between, say, 5% and 50% or something like that.
One certainly could. You probably have to. The hard thing is it's probably sensitive to the expense of the comparison operator as well. But you could certainly do switches like that under the hood, as sort does for detecting order n squared.
So somebody pointed out to me this weekend. It tells you something about the kind of Memorial Day parties I go to. But he pointed out that for 3 items, bubble sort is actually optimal.
Yep.
That's actually what standard sort does.
What's that?
Well, standard sort actually, it depends on which one, but they usually switch to insertion sort, which is essentially bubble sort, just the other way around. They actually switch to insertion sort for either less than 16 or less than 32 elements, because even though it's n squared, that's the fastest there.
So the fellow that I was, I love telling this story. The fellow that I met at our Memorial Day party. I'd worked with him at Microsoft many years ago, and one of the things that we did was we had these puzzles out on the table, and while you're waiting for your compiler or your build or whatever, or maybe you're just taking a break, and people would work on puzzles for a while. And I walked up to him once. He was working on a puzzle, and the puzzle, huge puzzle, was almost finished, right? There's only like 7 pieces left, and so it was, of course, the middle of the sky, which it was all, impossible to go by color. And so what he was doing is he was brute forcing. He was trying every possible combination to see how these things would fit in, which I think is how you finish up a puzzle, right? And there's nothing surprising about that. But what he did was he turned and looked at me and he said, for a small enough value of n, any algorithm is acceptable.
It's true. It's true.
Yeah.
And I think it would take a programmer to make that observation about a puzzle, but that's what we're figuring out, I guess.
Yeah.
All right. So this is sensitive, which some of the variables that he did not, that Thomas Guest did not control for, were how expensive is the comparison operator. I mean, obviously, if you're talking about comparing integers, the comparison operator is trivial, right?
Mm-hmm.
But that's not the general case. Comparison operators can be non-trivial depending on the data you're doing. Is there? I mean, I'm putting it to you, Howard. I know you're no longer maintaining lib C++, but if you were, I mean, sort is a kind of, well, I should say, we're not talking about sort. We're talking about partial sort. So maybe partial sort's not used all that much, but is there something that should be done?
Well, that's a good question for the implementers. And
I understand you're no longer an implementer, but if you were an implementer,
great way to push that through. I don't think there's anything to be done on the specification side, on the standards.
No.
But Malte here is actually our currently the biggest sort expert in the room right now, having just gone through all this great work that he's done. And so, yeah, people should do their own research and experiments, and when they find something that appears good, let your standard lib vendor know, and or contribute to an open source implementation of it. And that's how we make things better.
Okay, so let me say this. First of all, I encourage everyone to read Thomas Guest's blog. There's a graph in there, which if I was good at this sort of stuff like Jens is, I would have that graph to show you. And in fact, if I thought about it, I probably could have made a static picture like that. Could have worked. I don't know if I could play video like Jens does, but I could have put up a static picture. Definitely go to the Thomas Guest blog and read the blog. It is very interesting, at least if you're at all interested in algorithms or sorting. It's very interesting. And then think about the fact that Howard pointed out there's some things that he's not controlling for, like cost of comparison operators and things like that, and he's not doing anything other than 10%. So those were kind of givens. But one of the things he does is, after showing you the graph, he then does the analysis and shows you why it is that instead of getting essentially n log n with partial sort, he's pretty much getting something close to order n on a partial sort, which is pretty amazing. So definitely look at it and read it. Okay. So I'm going to ask Malte 2 questions. The first one is, before we get to Radix, just looking at this, do you think there's something we should try to get partial sort fixed to do this? And do you think this is valuable enough? I mean, is the Thomas Guest case too much of a special case?
No, I think it's actually it's actually the default case. I think end element will be faster than heap sort, except a partial quicksort will be faster than a partial heap sort, except in very rare cases. I think actually, by default, the quicksort will be faster than the heap sort.
Okay.
So even like maybe like if there's yeah, I think you would have to try pretty hard to find a case where that's not the case.
Okay. I will say I should have reached out to Jonathan Wakely. I didn't, but I did talk to Marshall and I talked to STL and invited them both on the show. And in principle, they were happy to be on the show, but they had conflicts. So we'll work with them, and we'll see if we can get them on the show. But we have a call out to them and say, you have a potential situation here that we can improve partial sort. Okay. Now we get to the second question. from Malte. And I guess this isn't as much a question as I'm just going to ask you to tell us about your work on radix sort. So I've got links in the video notes to your blog, Probably Dance, and you've been talking about, first you talked a little bit about some heap stuff, not heap, but hash stuff that was interesting. But let's talk about radix sort, and maybe we can get to the hash stuff later. Let's talk about the radix sort first. So tell us about what radix sort is, why that works, why that's so much better than a regular sort, and then also why it's not general, why you can't just generally use it, and then how you've managed to finesse that. Okay.
Yes. Okay. So yeah, radix sort is it's actually a well-known old algorithm. I think most people learn it in school at some point. Like I had heard of it for a long time, but just never actually knew how it worked. It's a special case sorting algorithm that in the vanilla form, it can only sort integers. But like the reason why it's interesting is that it can sort integers in linear time. It's faster than n log n. And yeah, let me see, how does it work? Well, it's a bit hard to explain without visual aids, so I'm not...
I know this great article that explains it very well.
Yeah, I mean, actually, I just gave a talk about it, right? So like as soon as the talk is online, which I think Jon can tell us when the talk will be online. In the talk, I walk...
Hang on one second. Let me interrupt because you brought this up. I forgot to make this announcement. The talks for C++ Now are being uploaded as we speak. However, they're uploaded in private mode, so you can't see them yet. But very, very soon, we're going to make them all public, and we'll make an announcement and say they're online. So thank you very much for mentioning that. The other thing, while we're doing announcements, which I should have done at the beginning, I'm sorry to interrupt you in this, CppCon submissions deadline is in a week. So get those in. I'm looking at you, Howard. Get those submissions in. And I will also point out that at CppCast, which was a great episode, the guest was Richelle Bilderbeek, and he was talking about Travis CI, which was very interesting to me. I'm going to reach out to him about doing a workshop on that at CppCon. But they misspoke on there, and they said that the deadline was July 11th. It is not July 11th. It's June 11th. Do not wait. Get your submissions in. Okay. Commercial over. Malte, I'm sorry about interrupting. Back to you.
That's good. Okay. So yeah, I then won't go into too much about how it works. I'll just in the talk I explain like from very basic steps all the way through to the end, like how complete radix sort, and I generalize it all the way until it can sort most things, and then I also talk about how to make it faster than it was before. But so before I came along, radix sort could already sort integers and strings. People had generalized it to sort strings, and somebody had also done, I think his name is Michael Herb. He had done work to generalize it to floating point numbers. And the way you generalize it to floating point numbers is that if you just reinterpret cast a floating point number as an integer, it will actually sort in the right order as long as it's only positive floating point numbers. Because if you reinterpret cast them, like the highest bit will be set because that's a sign bit, so like they will come in the wrong. They will come after the positive numbers. So the trick you do for that is you just flip the sign bit, and then they will sort in the right order. Now the negative numbers come first, then the positive numbers. The second problem you run into is the negative numbers. They will sort in the wrong order because they just have different bit meanings than integer numbers. So what you do for that is just for negative floats, you just flip all the bits, and like that you generalize it for so then when you want to sort floats, you just reinterpret cast them as you want to use them in the radix sort, and like that you can sort floating point numbers in linear time. And then you reinterpret cast and do the bit flipping tricks with like flipping the sign bit or flipping all the bits depending on what the float is. And then so that was the starting point for me, and I need to explain a little bit about how radix sort works, because radix sort sorts one byte at a time. It sorts integers first on the highest byte, and then sorts on the second byte, then sorts on the third byte, and then on the fourth byte. If you have 4 byte integers, if you have more, then it sorts them more bytes at a time.
So let me see if I can clarify the reason. The magic of the radix sort is that the way it's sorting is essentially by assigning things to an offset in an array, correct?
Yes,
and so that's
yes.
why it's so important that everything be somehow be mapped into an integer, because it's basically got to take the data and map that into an offset, right?
Yes. So the maybe I can explain the magic of Radix sort for 1 byte, because that's also how I started the talk. So the trick is, if you're sorting just a single byte, then what you can do is you can, like, you know that there's only 256 possible values that each of those can have. Like, let's say I have 1 million bytes, I want to sort them in so all the 0 bytes come first, and all the 1 bytes, all the 2 bytes, etc. Right? It doesn't come up that often, but let's say I just want to sort 1 million bytes. And so what I can do is I can just count how many 0 bytes are there, how many 1 bytes are there, how many 2 bytes, etc. And then once I have all those counts, this would be much easier with visual aids, but
well, you just pass the array and reconstruct the data based on the counts.
Kind of, yeah. So what the counts can tell you is, if you add up all the counts, you can know how many numbers will come before me. So you have like an array, you have all the counts in there, you add up all the counts, and then if you index at index 5, you can see, oh, there's number 2000 there. That means there will be 2000 numbers of all the lower values, because you've added up all the counts to that point. So there will be 2000, like maybe a couple hundred 0 bytes, couple hundred 1 bytes, etc. But at index 5, the number is 2000. This means up to this point, everything adds up to 2000 values will come before me. So you can index at constant time. You can just ask how many values come before me, and I just put myself at that position. And that's the magic of Radix sort. You can like kind of compute what is my offset going to be, and you just put yourself at that offset, and then there's no, like, other sorts kind of like shift things back and forth slowly, and Radix sort just puts it exactly where it has to go. And now the trick of Radix sort is that there's so this 1 byte sorting is pretty easy to understand, and it's called counting sort, the algorithm. You can already generalize counting sort to sort more than just 1 byte values. You just have to somehow provide a sort key that's only a single byte in size. Right? So if I say I want to sort strings only by the first character, I can just return the first character. That's my sort key. That's a single byte size. So that would work. But then Radix sort then takes this counting sort and says, I'm just going to sort 1 byte. I'm going to sort first on first byte, then on the second byte, the third byte, and just going to go all the way through. It's a little bit tricky to do that. It's not quite trivial, but it's not super complicated. Like to just say, instead of sorting a single byte, I'm going to sort 1 byte at a time. But yes, for all of this, you have to like, bytes have to have a similar meaning to integers, because you want to use them as an index into this counting array so that you can add up all the previous counts before, and they have to come in the right order in the counting array. And floating point numbers were tricky because their bit pattern is more complicated. But like strings and integers were easy. But anyway, so somebody had figured out floating point numbers before me, and somebody had figured out strings and ints before me. And then so what my work was that I said, if I can sort ints, strings, and floats, then I can also sort tuples of ints, strings, and floats, because I can just like go on to the end of the first int, then go on to the first byte of the second int, and like that I would sort tuples. And once I can, and then if I can sort tuples, actually I can also sort vectors, because I can just go through the ints in the vector. And once I can sort ints and tuples, ints, floats, strings, tuples, and vectors, and I can compose them however I want, then I can pretty much sort anything. Now the other thing I did is I wrote my Radix sort with an interface where you have to provide a sort key. So you have to. So I ask you, instead of providing a comparison operator, I just say, what do you want to be sorted by? And you have to somehow like return me like either an integer or like a float or a tuple or something that says I want to be sorted by this thing. So maybe you return like 2 of your members, and say by these 2. You just return them in a pair. And so then what I claim is that like once you can sort integers and floats and pairs of those, and you can return them from your own sort key function, I say you can sort almost everything, because you can build almost anything out of tuples of these types. And so basically, I mean, I found a few cases where I couldn't quite apply this, which is like things by like Unicode. You can't, like, that's not so easy, or case insensitive sorting of strings, or somebody in my talk brought up that rational numbers wouldn't be sortable like this, because they can be compared, but you can't easily return a simple sort key for them. Things like that. So there's a few cases that you can sort, but I claim that like 90% of what you want to sort, you can sort with Radix sort like this. And so,
wait a minute. Why couldn't rational numbers be sorted? I mean, if you can sort floating point numbers, then it sounds to me like you can convert a rational number to a floating point number pretty easily. Am I missing something there?
You could do that, yes. But you might, like, if you have very big rational, like if you have, okay, yeah. So rational numbers work as long as they fit, as long as you don't lose precision when you convert them to floating point, right? But if you have, if you had like, if your rational numbers were big enough, like big int rational or something, or actually big integers in general probably are difficult. Maybe, I don't know. Like, so, but most cases you can sort with this. So that's what I wrote up in the blog post, and I also optimized Radix sort a little bit compared to how fast it was before, and that also always helps to get more attention, because then people are like, hey, this is faster. That's nice.
Okay.
And so like that, like I have been able, like at least in my own work, I've been able to replace all my uses of standard sort with Radix sort now, and it just makes everything faster. Like, because it's almost linear time. The algorithm I end up with is not quite linear time, but it's almost O of n, and it's much faster than log n sorting.
Okay. All right. So let me make sure I understand what you're proposing, or maybe you're not actually proposing this, but I'm jumping ahead and saying, so we can make a sort algorithm that has the exact same signature as standard sort. In other words, you're not passing in a sort key. Instead, the algorithm can look to see in a type traits kind of way to say, is there a sort key defined for this data structure that we're trying to sort? And then if that sort key is not defined, then we fall back and use standard sort, whatever it's called, intro sort or quick sort or whatever it is. But if a sort key is defined, then we can use Radix sort and get what is likely to be much better performance. So it's not general in the sense that anything can be sorted this way. You've already identified a couple of things that maybe just don't sort, at least not in a straightforward way with Radix sort. But it's an optimization. It kind of reminds me of, I'm an old MetroWorks user, and MetroWorks in the standard library had some ability to do things that we now do in the standard, because it's part of the standard now. But it used to be that you could have MetroWorks extensions that you would say, for this data type, it is safe to do trivial copies and things like that. Am I getting that kind of right, Howard?
Yeah, I agree. This is very interesting work, and I think it could go under the hood as standard sort.
Yeah.
So we would make some kind of standard type trait that is the sort key, or maybe we'd have to call it the Radix sort key or something like that. But we'd say this is the sort key for this type, and the default might be that there isn't one.
Yes. You can actually also. I have a customization point like that because I needed it because I needed a customization point like that already for nested types. They were more complicated to extract the out of. But what I would do for the standard is I would say I would keep standard sort, and I would say if as a last argument as a comparison operator, if you provide a function that takes 2 arguments, then it's the comparison operator. If you provide a function that only takes 1 argument, then it's the extract key function. So you do a compiling, you check the function object that got passed in. Does it take 1 argument? Does it take 2 arguments? If it takes 1 argument, then it is the extract key function. It's a sort key function, and it would it would use Radix sort.
Why is that better?
It's just in case you want like more than one sort behavior per type or something. If like maybe once you want to sort ascending, once you want to send descending. It's just it is probably, you would probably want both. Like you would probably want, like, just say for this type, here's how you sort it. Like provide here's the Radix key function, and then but also you want to like offer a customization point at the point of the call, because you want to. Maybe you're dealing with a type that you don't have control over, like some type from a different library that you can't extend yourself, things like that.
Well, but a type trait you could extend yourself. mean, that's the whole point. That's the neat thing about type traits, is that anybody could do that, right? And also, what's nice about it is you could do what Howard did. So I may not have quite explained this correctly, but the type traits that Howard allowed users to define, those type traits were in the MetroWorks namespace. So what was happening is Howard was allowing users to define type traits for their own types, which didn't affect the STD interface at all, but the implementations would be faster, right?
I think you.
Yeah, that makes sense. Yeah.
One and only person who noticed that, John.
I thought it was brilliant, because one of the things that was nice about it was that I could write completely portable code. In other words, I could take the code and I could run it on a non-MetroWorks implementation, and it still worked. It never affected correctness. It was still correct. However, if I use the MetroWorks standard library with my MetroWorks only extensions, I would get better performance. And I just thought that was such a clever implementation, and it's one of the reasons why I'm such a big fan of Howard's. Anyway, but I'm thinking we could do the same thing now with the standard.
Yes, I agree.
What I'm saying, what I mean is that a standard library implementer, like Howard used to be, or Marshall, or STL, or Jonathan Wakely, they don't need permission to the standard to say, I'm going to make an extension. I'm going to make in the GCC namespace, here's a type trait, and if you define this type trait, I'm going to use that to do sorting, and if you don't define it, I'm going to fall back and do standard sort. Arguably, somebody could say, well, the standard doesn't say that this is going to happen if this is defined, but it's certainly it's certainly in the spirit of portable code, because you're going to get the exact same result as if that wasn't defined at all. You're just going to get it faster, right?
Well,
I think that's a good idea.
Also, the implementer could just go ahead and define said type trait for common types like ints and strings, so that the user doesn't have to do anything at all for common cases.
Sure. And in fact, that's what the standard would do. I mean, if this ever got to the point where it was standardized, obviously the standard library would create the sorting key for, first of all fundamental types, and secondly, all the things in the standard library, just like hash is defined, right? There's a standard hash for certain things. And if it's in the standard library, then, I mean, even, I think, error codes, there's a standard hash defined for it, right?
Yeah.
So,
I think that's a good idea. I think something like that should happen. Yes. I'm probably not the person to do it, because I'm kind of actually over working on Radix sort at the moment. I need a break from it, especially like after giving the talk, which was a lot of time for me. Like I spent a lot of time on that. Yeah, I think somebody should. I think it's a good idea. Yes.
Do you think that this would be looked at favorably by the standards? You're still involved in the standards committee. You're just not the chair of the library group anymore, right?
Me? Yes, I'm still involved.
Do you think that this is the kind of thing that the standards committee would smile at?
I doubt it. I think this is more implementer territory. That implementers could do this or not, and do it under the hood, and without affecting the specification.
Well, except that as Malte just pointed out, you have this situation where you might want to, for example, you might want to do a descending sort, right? And you need a way. You would really like to have, and I didn't understand this at first until he gave this example, but you really want to have a flavor where you actually pass the key sort in, because the sort key, function in, because of the fact that you might not. I mean, there might be exceptions to the general rule. Say, this is how I always want to sort this thing, and so that's something that the standard library. If you're going to change the interface, right? I don't think it's. I mean, an implementer who added that, which I assume an implementation certainly could, but that would make the code not portable.
Right.
Yeah.
So you know, it's always tough to tell what the committee's going to do. I certainly have no clairvoyance, and so I don't know. Maybe the committee would love it. Maybe they would not like it. I don't know. The committee certainly welcomes proposals on all areas, and so I wouldn't want to discourage anybody from submitting such a proposal. It's
There's
difficult for me to predict how it will be received.
There's actually one reason for like definitely changing the standard, which is that the standard has no sort copy. It has no standard sort copy, no copying sorting algorithm, which you don't need for quicksort. But in Radix sort, there actually is a faster Radix sort if you copy the data from one array into a different array.
Mm-hmm.
And that one, in my benchmark, that one can be like 5, 6, 7 times faster than standard sort. So it's like, it's even faster than the one that I presented at CPP now.
Right.
So adding a copying sorting algorithm to the standard, that would require a change to the standard.
And that would also be something that would be useful even if you weren't using Radix sort, because you might have a const set of data that you would like to make a copy of and then sort, and that's going to be more expensive than sorting it into a new home. I think that would be more expensive even if you weren't using Radix sort, right? I mean, maybe there's no better way to do it for other sorts and you make the copy and then sort. But.
Yeah, actually, the way that the copying Radix sort works is that ping pongs between the two. You can use it for const data because you need to, like, you copy first from one buffer to the other, then back from this one to this one, and from this one. So you copy back and forth between the two buffers. So both buffers have to be non-const for it to work.
Does that mean you modify the original buffer?
You do, yes.
Well, that's
and actually you don't know ahead of. You don't necessarily
copy to me.
No, it's not. Yes, it has kind of weird semantics, because actually the way I implemented it is that I return a Boolean which tells you which of the two arrays the data ended up in, because I don't actually necessarily know ahead of time which of the two arrays the data will be in at the end. And so it has
how many, whether it's an odd or even number of bytes you have to sort on.
Yes. So actually, I do know at compile time, but it depends on what type you pass in. Like if you pass in an int, that's fine. If you pass in a pair of bool and float, then it would be 5 bytes. So it would be they would end up in the original buffer again at the end, because you ping pong back 5 times.
Okay.
But that one's really fast. So I think I don't know where it's. Well, it's useful if you have the extra memory. Just like if you're doing something. If you double buffer anyways for other reasons, then you would. I don't have a real use case for it, but since it's so fast, like it's literally like 5 times faster than standard sort in many cases that I've measured, I think it would be worth providing. Like it might be something good to provide.
Yeah. Okay. So unless there's something more somebody wanted to say about the Radix sort, which I think is a very interesting idea. And I'm glad that you figured out how to really generalize it for us. Let's talk a little bit about hash, because you also did some work on probably Dance on hash functions. So you want to talk about what you did there? We don't have a lot of time left,
yes.
But we can talk about this.
Yes, yeah, I worked on a hash table. So the problem with the standard unordered map, well, a problem with it. It's not like the problem. It's not a big problem, but it's a small problem that bothers some people. Is that every single node is separately heap allocated, right? If I have an unordered map from int to int, and then they're all separately heap allocated, it's just not nice. So the and actually, like it also makes it a bit slower, because then what happens is when you want to look up an item, you have to look up the index in the internal array, and then like chase a pointer to a heap allocated node, and then there's actually a linked list behind that. So maybe you have to like chase a linked list of pointers of nodes, and that's slow. So the idea is, and this has been done many times, is to use a what's it called, open addressing hash table, where you just have one contiguous array and you just index into there. And so I implemented it open addressing hash table, like, so none of this is actually anything I invented. I made a tiny improvement at the end, but it's called, there's a method for doing linear probing in an open addressing hash table called Robin Hood hashing, where what Robin Hood hashing does, let me first explain the problem. The problem with linear probing, so linear probing means when you have an array, when you have just one array for the hash table and you put a piece of data in there, and then you want to put another piece of data in there, that slot might already be taken because like maybe two values hash to the same index. So in linear probing, what you do to resolve that is you just, when that slot is full, you just go over to the next slot. And that one's also full, you just go over to the next slot. And that's a good approach, and actually many hash tables do that, but there's problems with it because you can easily end up in bad situations with that. And so Robin Hood hashing guarantees that you always get the ideal optimal layout. Like every single object is as close to the best position it could be in as possible, considering all other objects. The method for doing that is pretty simple. It's just as you walk along through the table trying to find a free spot, you check how far is this object from its ideal position. And let's say this object is like 2 slots from where it wants to be, and I'm currently looking 3 slots from where I want to be. I'm just going to take his slot because I'm further away from where I want to be than he is. And then I move on to the table trying to find a new slot for the other guy. So you're just like walking through the table trying to find the best slot for everyone. And like if you find someone, the reason why it's called Robin Hood hashing is that you take from the rich slots and you give it to the poor slots. So anytime you find a rich slot which is close to where it wants to be, you just take its spot and then find a new spot for the previously rich spot, which is now a poor spot. So as you insert things, you reshuffle things in the table, but then lookups are really fast because everything's as close to its ideal position as it can be. And you also have everything in one contiguous array, so it's nice. It's nice for caching effects and all that stuff. So supposed to be pretty fast. That being said, this took me like 3 different hash tables to write before I got it right, and it actually took me like years because I gave up on it at some point. Because what happens is the reason why everyone uses node-based containers, and I only found this out after I tried implementing all this, is that in benchmarks, node-based containers are really good. And actually not only in benchmarks, but often also in the real world. If you just iterate a lot on your table and you do like a lot of work on it, node-based containers are actually really good. And the reason is that node-based containers can make the inner loop really tight. And what you do is you look up the pointer, and then you compare the key. And then you look up the next pointer, you compare the key. You look up the next pointer, you compare the key. That's like, it's literally just like those 2 instructions alternating. And in a open addressing, you look at the first pointer, and then you compare the key, then you go to the next item, you compare the key, but every time when you go to the next item, you have to also check, am I at the end? And if you're at the end, then you have to like wrap around to the beginning. And you actually have to do even more checks because you have to check for like tombstones and like special values. So the inner loop for open addressing and also for Robin Hood hashing is actually not quite as tight as the inner loop for node-based container, where it's literally just look up pointer, compare, look up pointer, compare. So the let's see, so then in benchmarks, you're basically only measuring this inner loop, and actually what you're really doing is the most common case. So as I talked earlier, how you like have to walk through a linked list in an unknown map because like it's all separately heap allocated nodes. The most common case is actually that you find the element immediately. So immediately on the first lookup, you find the element, you're done. Or immediately on the first lookup, you say, like, oh, this bucket is empty, there's nothing here, I'm done, right? So you actually want to optimize for the first, you actually want to optimize for that case. You want to optimize for the case where in the first lookup, you find immediately what you're looking for. And so the open addressing, it's optimizing for if you have to iterate through the list, right? Because then it's like, oh, then you have to worry about the cache and all this stuff. But that's not really the case that you have to optimize for. You have to optimize for the very first lookup. And node-based containers have a very simple first lookup. So what I did, my contribution, is that I found a tiny tweak to Robin Hood, or not to Robin Hood hashing, to the way to write an open addressing flat hash table that makes my first lookup really fast and makes walking through the list really fast, where I don't have to do any bounce checking. And so what I do is I say my elements can be at most a fixed number from their ideal position. And like people quickly pointed out to me that this had been done before, but I couldn't find it ahead of time. So I did independently reinvent it, even though it was done before. But so I say when I insert an element and I'm like looking for a free spot, let's say at first I say it can be at most 4 spots from where it wants to be. If within 4 slots I can't find a free slot, then what I do is I grow the table and then I try again. And every time I grow the table, I think I increase 1 slot. So after growing the table, I can say now it can be at most 5 slots. So and I just do log n extra slots. So it can be almost log n of like the whole table size away from its ideal position. So if it's more than 5 slots from its ideal position, I grow again and then reallocate. And so what that does is that I can at the end of the, instead of, I never have to do any bounce checking now, because the trick I do is that when I grow the table, I know that every element can be at most 4 or 5 or 6 or some number of slots from its ideal position. So just allocate that many extra slots at the end of the table. And then when I insert elements, I just, I know that I can never go over the end of the array, and I never have to wrap around to the beginning of the array. And that removes 1 check from my inner loop. And that makes my inner loop exactly the same number of instructions as a node-based container. And then I'm just as fast, but I also have the same caching benefits that you get from an open addressing table. And that's not quite true, actually, because there's one thing that I still don't handle where I'm sometimes slower, which is that with Robin Hood hashing, what happens is, since objects can get pushed around, oftentimes the first, like let's say there's like 2 slots right next to each other, and I try to insert an element to the first slot, and I try to insert an element to the first slot again. Now this one went 1 over. If I want to insert 1 into the next one, this one has to also go 1 over. So the common case in Robin Hood hashing is actually that you don't find it in the first slot, you find it in the second or third slot, because because objects keep on pushing each other away. So I actually typically find my things in the second slot, or like I usually find them very close to where they're supposed to be, but not directly where they're supposed to be. But it's still pretty fast, and it's usually faster than node-based containers. There's like one node-based container written in C called khash that is sometimes faster. But once your table gets large enough, like mine is faster, because once your table gets large enough, you benefit from the cache locality.
But one of the trade-offs we're making here is that there's a guarantee in the standard unordered containers that once something goes into the container, it's never moved. Its address is always the same. And you're changing that in a pretty fundamental level, because what you're saying is that it's like a vector in how it's stored, meaning that adding or removing items can invalidate addresses.
Yes, yeah, that's a trade-off. Yeah, I think that's. I think the standard, the standard made the right decision because they wanted a drop-in replacement for standard map, and standard map gave that guarantee, right? And so they wanted, if you just replace standard map with unordered map, everything will work. So I think they made the right decision. But I think if you want, anyone who writes a fast hash table will do an open addressing hash table, and the standard did not do that. Well, it depends actually. Like as I learned with all this, like node-based containers do have their benefits, but it's actually the one in the standard is surprisingly slow. Like in all the standards in all the standard implementations I've found, I've tried the Visual Studio one and the GCC one, and their node-based containers are surprisingly slow compared to other implementations that are available. I don't know. I don't actually know what they do as extra work in there, but anyways, yeah. Some people, if you go online and search for fast hash tables, they're all using a single contiguous array, and
they're not using nodes, which makes sense. The overhead of adding a container is expensive if you have new nodes.
Yes.
Howard, do you have any comments on the way that the standard went for unordered? Is it just that they?
I think it was Matt Ostrom that introduced the unordered containers, and I could be mistaken, but I think I remember him saying once that his intention was to allow both chaining and open addressing implementations, and that it was a mistake that the reference stability requirements actually prohibited the open addressing. That being said, I think it was a fortuitous mistake, because I do think that is important. The fact that Malte mentioned it, it needs to be a drop-in replacement for map. I do think that is an important requirement. But I'd also like to say that, just like we've got both vector and dec, it doesn't mean that we shouldn't put an open addressing container into the standard. It's another wonderful tool in the toolbox.
Right.
Named, I don't know, hash set instead of unordered set or whatever. We could think of a different name for it. And personally, I think it would be a good idea to have that solution, that tool in the standard as well.
So this is yeah, and it's kind of like boost flat map, right? Where the trade-off is it's not stable in the same way, but it's better performance not than a hash, but it's better performance in a tree, right?
Yes.
So here's my question related to introducing the unordered: is why is there an unordered multi-map and multi-set? Those inherently have collisions. I once, as a little trivial exercise, I wrote this, I trained, right? And so I wrote this little example application that was written in classic C++. I said, okay, now I'm going to modernize it. And I added a bunch of, I put in some range-based floors and all these, to modernize it. And one of the things was I changed my multi-map into an unordered multi-map. And my performance just fell on the floor. I was like, what did I do? It's supposed to be faster. And then I realized, oh, wait a minute. This is a multi-map. It's got tons and tons of collisions. And those collisions killed my performance. And I'm kind of wondering why those containers even exist. I mean, it's the same sort of thing as saying, why is there no push front on vector? I mean, yeah, you can do it, but we want to make clear that that's not a good idea. And I would argue for the exact same reasons that multi-map and multi-set, unordered multi-map and multi-set just shouldn't exist.
Well, that's an interesting observation. I would have thought that there would be use cases where the number of equal ranges is both short enough and rare enough that there might be a win. Yeah. But I'm sure that varies from application to application.
Yeah, I can see that. I mean, if you had a situation where you say, well, theoretically, there can be collisions on the key, but they're going to be so rare that we can handle that. And if you actually had that situation, but that's kind of like saying, well, if you want to do push front, you only have 2 items. That's not that expensive, right? I mean, it's
granted.
It's kind of saying, yeah, there's a special case where it makes sense, but I'm just saying, for the naive user, which I was and shouldn't have been, I created this unordered multi-map, and it was just out. And I actually thought my app was broken. It's like, well, did this hang? What's going on? And then, a minute and a half later, it finally finished. It's like, what happened? And this was with a trivial amount of data. I mean, well, I shouldn't say that. It was probably 30 or 40 text files with non-trivial length. I was doing all of Shakespeare's work, and I was indexing it.
Yeah.
And so there's a lot of, almost every word is going to be a collision.
Mm-hmm.
Right. So anyway, so I think we have come to the end of our allotted time, and we don't want to overstay our welcome. But I want to thank both of you for being here. If you're interested in algorithms at all, this was a very interesting discussion, and I want to thank both of you for helping to inform me and help me to think about things a little bit better.
Thank you for having me. It was a delight to be.
Yeah, thanks for having me.
Thank you, and want to have both of you back soon. I will say also, my plan is more or less to have another one next weekend, another show. But after that, my wife and I are going to be on a bit of an extended vacation, so we'll be gone for at least 3 weeks. So
have a good vacation.
Thank you very much. In case we're not on next week, and even if we are, get your submissions in. We're almost out of time on that. And late submissions are possible, but they're going to be harder to get approved. So so get those submissions in. And anyway, until then, I'm going to thank my guests. Thank you, Howard. Thank you, Malte. And I'm going to say to everyone, safe coding, and we'll talk to you later.